So it's the same idea of standard deviation helping me figure out how relatively big or small some difference is. All right. I have to make it relative. So I don't know how big of a difference these are until I divide it by what I expected to happen. I can see how relatively big these differences are. And these differences are not relatively big. So if I expect 7 and I see a difference of 28, well, that's 4 times as big as around what I expected. So that difference would be relatively big. These are relatively small differences. All right, let me stop here for a second. I think what should make a ton of sense is that we check to see how different what we see is from what we expect. That step is like, yeah, Jeff, that's a good first step in anything. See how far things are. Square it to kill the negatives, like we had to do before. This step is the one I told you might be a little freaky, but it really is just getting it to be a relative difference. So if I give $5 to somebody who only has $5 in the world, that's huge. You just doubled all the money they have in the world. You with me? If I give $5 to Bill Gates, is he even going to take the time to reach out and pick it from my hand? That's not going to be worth his freaking time.
Oh, that's not.
I don't know Bill Gates. That's what I expect you would say to me. It's $5, Bill Gates. And then he moves on. Are you guys semi with me? So relatively, how big is the difference? That's what I want to see. So what would all these be if they were exactly the same? If they were exactly 7s, these would all be 0s. Yes. So what does 0 mean on this picture then? The closer I am to 0, the smaller the difference is relatively between what I see and what I expected. So then there's this cutoff amount. Can you guys verify the 11.071? Where did I get that shit from? Well, what? Now here's where, okay, here's the next thing. This is called the goodness of fit test, by the way. That kind of makes sense. I'm seeing how well my observations fit to what I expect. So we call it goodness of fit. Just to really make it sound like we don't understand grammar. Degrees of freedom for this test won't be 42 minus 1. How many categories are there?
6.
6. So then degrees of freedom is categories minus 1. So in the book you'll see it as K minus 1 because they didn't know how to spell categories. Not really, it's because we use K anyway. But just, it sounds good. All right, so everybody, so I warned you when we first talked about degrees of freedom, somebody asked, is it always that? And I was like, well, no, it's not always N minus 1. Here it's K minus 1, the number of categories minus 1. So can you verify the 11.071 I got? Alpha's 0.05. Right? Goodness of fit tests are always a one-tailed test. You just have to be far away. So if you look up 0.05 for degrees of freedom of 5, do we get that? You have 0.05, 5 degrees of freedom. There's the 11.071. That's where I got it from. That's where that came from, and there it is on the picture. I made a computer do this for me, so you didn't have to suffer through my horrific drive. And of course, we compare that to, so this formula here, all become a thing. I always forget to make this big ass here. That formula is like another iteration of that, just like z-scores have several kind of iterations. These follow that Jabba the Hutt picture. These follow that Jabba the Hutt picture. Just like the normal curve exists, and then we have a lot of z-score formulas that kind of like fall into that picture. That picture exists, Jabba exists, and then we have a bunch of formulas that fall into that picture. So 0 would mean, let me see, for those of you at home, 0 would mean that there's no difference at all. Oh, get out of there. Become better. Become better. That's good. 0 would mean no difference at all. There's a certain cutoff that is just so far away from 0 that's evidence that there is a difference. Do you guys get a feel for that? Randomly, I could happen to get some that are different from 0, but if I do a sample, it's got to be so different as to say something about the whole population.
So
Yes.
relating that to that's a problem because
Yes, so we calculated, we got a cutoff of 11.071. There's my rejection region, right there. Did we make it far enough away when we did the sum of these? No, we only got to there. So we failed to reject that they are the same. So we have not found evidence to reject the claim that they are uniformly distributed. Does that mean that they are uniformly distributed? No, we just can't say they aren't yet. I could do another sample, maybe a bigger sample or something, you know, and see if I find evidence, but at the moment we don't have the evidence. Maybe. This is all freaky shit. Yes, ma'am.
So the 5% is in the
Yes, just like alpha, I've got to give you the level of significance, the alpha. And where's alpha sit on our chart now? And to be really, really honest, the kind of problem we're doing, the goodness of fit, you only have to worry about this side. Don't those look like alpha values? Yes. So that's where you're going to look. So you guys try to do. Now let me start with alpha number 2. Let me do an example. Oh, here's the example I should have done earlier. Oh well, too bad, Jeff. Oh, this is the example I think is on the practice final. What if I expected 20% A's, 30% B's? What do you got, Jeff? 30% C's, 20%. How much is that? Yeah, 20% D's and like no F's. Right? Let's say that this is what somebody expects to happen in their class they're teaching, right? And then they're gonna face some hard realities, but it's good hope. So are you with me? This is what they expect to happen. So if they have 400 students total, what does that translate into in terms of hard numbers? How many A's do they expect? 20% of 400. They expect 20% of their students to make A's. Well, they have 400 students. So how many students? 20% of 400. And 20% of 400 is 80. B's 30% of 400 is 120. C's another 120. I'm sorry. Yes, they're another 30. And then D's is 80 again. And no F's. What can you do to make sure this is 200, 400 total? Then I have to tell you, so you can do this for this problem. You see how what you expect to have happen with cholesterol levels? So you can fill in the expected column. Then I've got to tell you, well, if I see 62 A's and 97 B's and whatever else, do you see what I'm saying? Then you can do the observed minus expected squared, all the other stuff. So there's only 2 possibilities. Either it says that they're uniformly distributed, so they all should have the same number in them, or they follow some percentage. They have to calculate each one. So try to do that one about cholesterol levels. Woohoo! Man. As always, I hope any of that made some kind of sense. Yes, sir.
For the last one, is it divided by like the entire, like the expected total, or is it divided by each?
No, just divided by each. So each row. So you divide. So like up here, where did I get 0.571 from? 4 divided by 7. 1 divided by 7, bam, so forth. So in each row. I like it. So it's like it's not divided by the sum of each, right? Okay.